Yeah, hi.
Hello, Prasanti.
Yeah, tell me. Vinita, are you saying anything?
No, no, I was saying hello. I mean, you said hi. So.
Fine, fine. So in the last session, we have discussed on generate block, how to do the synthesis using file. We have discussed on latches, right? So did you got the clarity why the bad latches are inferring and how we can avoid the bad latches? And you have seen the circuit difference also after doing synthesis. So how it will be looking like for in RTL design if any latch is generated. So how we can avoid the bad latch. And did you work on assignments? Anyone? In generate block here we have given example like design a full adder using a ripple carry adder, or else design a ripple carry adder using full adder, and that too we need to use the generate block for loop. Did you tried anyone this example? What about Sumalata and Sai Kukurni? Lahari attended for the last session. Have you not tried? Or at least do you have any doubts in latches and generate block?
Doubts are not there, but I didn't try actually. I'm not feeling well.
Okay, fine. So today we are going to discuss on UDP. UDP in the sense user defined primitives. So how to write the user defined primitives. It is just like a topic, but in real time we never use UDP. Okay, because it's very old model where directly we put the truth table in the programming. Okay, so we never use this type of modeling, but we need to know about UDPs also, right? So that's why we can just work on a few examples with UDP. And today we are going to start with the test bench concepts. Okay, so you already developed lot of test benches, right? We already worked on different kind of test cases where initial blocks are involved and always blocks, dollar display, dollar monitor, and we also used dollar finish, and also to open the waveforms we already used dollar dump file, dump variable. So all these things, but we will discuss more detailedly. So how actually we are using these kind of like in terms of simulator directives, or how the test bench will be written in different ways. So we will discuss in the today's session. Okay, so first of all, UDP, user defined primitive. So in Verilog, it allows the designers to define custom primitive using lookup tables. Lookup tables are nothing but the truth tables. Okay, so they enable the specification of truth table for combinational functions and state tables for sequential. For combinational, we have a truth table. For sequential, we have a state table, right? So at the positive edge of the clock, which state should be high or low. Based on that, we call it as a state table. Okay, UDPs can be written for both the combinational and also sequential. It just define a behavior at a primitive level. Okay, so how we can write the user defined primitive, whether we consider a combinational or sequential. We'll see the example. So if you see the truth table here, I mean syntax, if it is a combinational logic circuit, suppose there is a multiplexer or a full adder. Okay, Okay, so for full adder, how many number of inputs will be there? A, B, C or the inputs and output. So for ABC, 3-bit means we'll have total 8 number of scenarios, 0 to 7. So from 0 to 7, we'll have some output, even it's a sum or carry. We have 2 outputs in full adder. So we need to define two outputs. But in a same program, we cannot define 2 outputs. Okay, because for each program, for each module of UDP, there will be only one output. Okay, even multiplexer we have only one output, or half adder we have 2 outputs, and encoders, decoders we have single outputs, right? Sequential logic circuits, sometimes we have single output. So whenever you want to define a single output, UDPs are okay, but even we can write the 2 outputs also, but we need to write 2 separate modules. For output 1 module, for output 2 second module. If there are 10 number of outputs, for every output we need to write every module separately. It's a very complex programming style we never use in industry. Okay, so if you see here, first we need to write input 1, input 2, input, like that, n number of inputs, and then output. Even output also we write directly according to the truth table. It never do any synthesis, it never calculate any functionality. Okay, we just put the truth table because we already know the output. That truth table we are directly putting here. Okay, and for sequential logic circuit, we need to mention input 1, input 2, n number of inputs, and what is the present state and what is the next state. Okay, we'll see the example so that you will get the clarity. So input terminals, inputs must be scalar variables. Scalar means you already know, single bit. Vector means multiple bits. Okay, other than one bit, like whether it's a 2-bit or 3-bit or 4, 5, whatever the number of bits are there, we call it as a vector variables. Scalar means single variable. Okay, single bit. Multiple inputs are allowed and declared using the input keyword. Order matters. Input entire, like we are using directly truth table, right? Order is definitely we need to follow the orders. Suppose ABC is a order. According to the ABC, suppose you are writing 0, 0, 0, 0, 0, 1, 1, 0, 1. Suppose for 0, 0, 0, output is 0. For 0, 0, 1, output is 1. For 1, 0, 1, output is 0. Carry will be 1, suppose. Okay. But if you interchange this B to C here, B here, C here. So 1 will be interchanged to here and 0 will be interchanged to here. But output will be same as we are returning using the truth table. Okay. So that's why we cannot interchange the any variables. Whatever the truth table is there, in the same way you need to follow the order. Okay. Next, output terminal. Even for output also same. Only one scalar output is allowed. Only one, that too scalar. That means single bit. That too single bit. So for combinational, UDPs are used as an output keyword. For sequential, reg keyword. As you already know, we use reg data type for sequential logic circuits, var data type for combinational logic circuits, right? Same way. And guidelines for using UDP. So just go through this guideline, whatever before I said, the same, how we are using the lookup table and how the outputs are defined. Next example, how to write the program. So if you see here, we are writing this program for full adder. Okay. So full adder truth table. What is the truth table of full adder? ABC inputs will be there and some carry output will be there. A, B, C, outputs sum, comma, carry. or carry comma sum. For ABC inputs, we need to write the variables, different scenarios from 0 to 7. According to the 0 to 7, we get the output for sum and we get the output for carry. Okay. So, as you already know the rules of UDP, we cannot mention these two outputs in the same module. Okay. So, that's why first we will write one module for carry. ABC inputs, carry is the output. Second module for ABC inputs, first one sum output, ABC input, sum output. Second one ABC inputs, carry output. Two different modules we need to write, and those two modules we need to connect in the top level. Okay. So how to write the program for UDP? User defined primitives. All these are user defined primitives. Okay. So if you see here, we need to write using the primitive only, not module and module. Okay. So primitive and primitive, same as a module and module. Okay. Next was sum. Here one output is a sum. So output sum A, B, C are the inputs. So input A comma B comma C and output sum. If it is a sequential logic circuit, then you can declare sum as a reg data type. Okay. But here it's a combinational logic circuit, right? No need to declare with the reg data type. Next, any time in UDP, whether it's a combinational or sequential, we directly need to mention the truth table. Okay. So that's why every time we need to follow this syntax, table, end table. Like in behavioral modeling, we write a case, end case, or in generate block, we have written generate, end generate. Like that, we write if else statements, right? So in the same way, we need to put table, end table. Okay. In the table, end table, we need to mention all these input and output scenarios. For 0, 0, 0 input, what is the output? For 0, 0, 1, what is the output? For 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1. Exactly truth table you need to mention here. Okay, same. However, we use case statement. Case is somewhat different. We put the control signals in a case, but here we don't mention any control signals. Just truth table, we just kept here. Okay. So this is for sum. Like that, in the same way, carry. Primitive and primitive. Input and outputs we need to declare. Output we need to declare, not outputs. Table and table. Okay. Within the table and table, whatever the output of carry is there, the input and output of carry, those outputs we need to mention here. Okay. So we got two different outputs, but where we need to run these two different primitives in the main top level module. So if you see here, this one is also for carry, C out, but different model. In Verilog, if you know the difference between case and full case and parallel case, just get the answer from your side. If you don't understand the difference between full case and parallel case, I will explain. Okay, you already know how to write the case, right? I think didn't explain that. Okay, see here, case. First, I will explain the case statement. In a case, we have two types. Just whatever we used before to model multiplexers or demultiplexers or sequential logic circuit, we just use the case statement. So if you see, this is one type of circuit for ALU, arithmetic and logical unit, where it performs arithmetic and logical operations. Okay, so module output OP, AB are the inputs, Z is also okay. OP is the operation, Z is the output, AB are the inputs. Okay. So parameter, you already know parameter. To declare some constant values, to define some constant values, we use the parameter. So add is equal to 2-bit binary 0, 0. So anywhere, wherever you use the add within the module, the add value by default, add will be assigned with a 0 value. That's what we call as a parameter. Parameter means a local declaration. Locally we will declare. But if you want to declare globally, that means outside the module. If you write outside the module, all the modules can access that value, that variables or values. But if you declare within the module, it's a local to this module only. That means within that module only we can use the parameter. Okay, whether it's a add or sub or a b c, whatever the variables you are considering. Okay, so why we are using this thing means, so suppose see here. First of all, what is mean by case? Based on the control signal. Suppose here OP is a control signal. For multiplexer, selection line is a control signal. Based on the selection line, we'll have the outputs, right? If selection line is a 0 0, then what is the output? First line will be getting first line data will be getting assigned to the output. Like that, selection line is a 0 1. Then D1 or I1, whatever the input you are taking, that will be assigned to the output. If selection line is a 1 0, then second line. Selection line is 1 1, then third line, 100, fourth line, like that, right? So in the same way, here OP is declared with a 2-bit size. 2-bit size means how many combinations will be there? 4 combinations will be there. 0 0 0 1 1 0 1 1, 4 combinations. Okay. So if I remove this 8th line, I'm just removing this 8th line. Okay. So here in OP, suppose I am writing OP 0 0 means OP 0 0, then Z is equal to A plus B. Okay. If sub is, if OP is a 0 1, then Z is equal to A minus B. And if OP is a 1 0, then Z is equal to A XOR operation of B. If OP is equal to 1 1, Z is equal to A end operation of B, suppose. Okay, logical operations. So here if you observe 0 0 0 1 1 0 1 1, if you do some simulation like that, it is difficult to understand because here we are not writing any particular name, string name. Okay, if there are more number of cases, suppose 8-bit, 3-bit means 8 scenarios will get 0 0 0 0 0 1 0 1 0 till 0 to 7. Okay, so in that time also, if you put all binary values, it's very confusion. But just seeing like this, we cannot guess what the functionality it is. Okay, so for that purpose, here we are writing some variables. Okay, we are just taking some variables. Suppose add. Add means by default we are assigning 0 0. Like that sub 0 1. Like that after XOR I have written, right? So I'm creating XOR. XOR is equal to 2-bit binary 1 0. Like that end. End means 2-bit binary 1 1. 2-bit binary 1 1. So in place of this 0 0, I can directly put add. Why? Because add is also nothing but 0 0. It already have 0 0 value. Like that 0 1 means I can put sub. 1 0 means I can put XOR. Like that 1 1 means I can put end. Okay, so see if you observe now how easy it is. But like just for practicing also, it looks very easy to understand. Okay, your code is understandable by everyone, anyone. You may get the doubt, here we already have plus, minus, XOR operation is there, and operation is there, so that we can understand easily. But instead of that, you are putting some complex expressions in a data flow modeling. Suppose there is a multiplexer. A multiplexer have some different style of programming. We write in a data, even it's a data flow, we can write in a array model, or we can write in a concatenation operator. There are a lot of ways, but we cannot know whether it's for a demultiplexer or a mux. Okay, so if you put 0 0 0 1 1 0, so that's why we can put like this variables we can use. Okay, and not only in that case, uh, and also suppose here you are declaring a 32-bit size. Okay, OP is a 32-bit size. Okay, so 32 means 31 down to 0. Suppose I am declaring here, and not only here 31, and here also AB or the 31 value, and Z also 31 value. Okay, so I am writing parameter n is equal to 32 or 31. Okay, so already here n value is equal to 31. This OP, AB, Z, we are using multiple times in the always block. Okay, so whenever you want to change every time, suppose instead of this 31 value, we want to increase the size of the array. Suppose we want to increase to 64-bit, or we want to increase to 128-bit, like that. Okay, so every time you need to change these 3 times, where even here we have written only 3 inputs, but if you written hundreds of inputs, every input we need to change 100 times, we need to change the value, right? So instead of that, if you declare like this parameter equal to n equal to 31, okay, so here directly you can put n down to 0, means what, 31 down to 0, and here also n down to 0, 31 down to 0, here also n down to 0, 31 down to 0. Okay, suppose in case in future, if you want to increase the value of n, suppose here you don't need 31 down to 0, we need extra memory to allocate the data, we need 128-bit size. Okay, so in that case, every time we need to change, everywhere we need to change 128 128. Okay, so if there are 100 of inputs, everywhere we need to change. So instead of changing there, if you change directly here to n, this n value will be substitute here, so directly it will be 128 down to 0, or 127 down to 0, or 63 down to 0. Based on your n value, it will be allocated the same. It's a constant. Okay, so this is how we declare locally. Locally in the sense of within only single module can use that variable. Okay, did you understood everyone what is mean by parameter? Hello.
Yes.
What about Tarun, Sai, Sagar, Akash?
Yes, ma'am.
Yes.
Okay.
Yes.
So suppose if you want to declare globally in the sense, we use the tick define. Here I'm using a define. This is a macro. Okay, same n is equal to 128. That means what? Not only this module, even if you are writing multiple modules, module 2 and module. Suppose in structural modeling, if you see, we write the multiple modules in the same program, right? One is for D flip-flop, and then for register we write. So module 3. Even in projects also, we use multiple modules in the same program. Okay, so whenever we are writing like this, module 1, module 2, module 3, all the modules wherever you are using this n, it will be assigned, because we are declaring as a globally. Okay, so that is what the difference between define and parameter. I think everyone got clarity about it, and we will discuss on case statement. Okay, so case in the sense same here. There are case op. Op is the operation, which is a 2-bit size. 2-bit size means 4 number of operations. You already know how to define the different scenarios here, and also we discussed yesterday how the latches will be inferred, bad latches or inferred in the case statement if you don't use the default statement, and why we need to use the default statement we already discussed yesterday. Okay, so another thing, case X and case Z. So case Z. So what is meant by case Z? We assign parallel values here. And case X. Case X is also at a time we use parallel values. Okay, so priority encoder is there. Priority encoder in the sense whatever the value we are clicking, whatever the value you have selected, based on that it will convert the binary value. Other than that, whatever the values are there before or after, it doesn't have any priority. Whatever we are using present, that value will be converted to the binary value. Okay, so if you see like a priority encoder truth table, same truth table will have the X. That means what? Here 1 is the highest priority. In these X, whether it will generate the ones or zeros, it doesn't, these all don't care. X in the sense don't care. Okay, then output will be 0 0, like that. X1 double X, output will be 0 1. X 1 X, output will be 1 0. So mostly in XOR we use the case X statement. Whenever you are using these X, you need to declare it as a case X. If you use like a normal case, it doesn't work. You need to declare it as a case X. Okay, in the same way, case Z. Z is also like a don't care. Okay, but we declare it as a question mark. 1 question mark question mark question mark. That means what? Whatever the values are generated, instead of question mark, it will generate either 0 or 1. Okay, so here 1 3 question marks instead of question mark. If all generated 0 or 0 1 0 or double 1 0, whatever the possible values are there, you can generate all possible values. We'll get 8 possible values in this 3-bit. So for all those, we are assigning 0 0. We don't need to write all possible combinations. Suppose here input is declared as a 4-bit size. 4-bit size means how many combinations? 16 combinations we will get. Okay, so instead of writing 16 combinations, if you write like this by putting question mark, we are generating parallel conditions at a time. Okay, so in that case, this case Z will be useful. Mostly we use case only because these also have lot of limitations. We cannot use in all conditions. Okay, mostly we use case or else parallel case, full case. Get the difference between parallel case and full case. You need to work on that and let me know by next session. What is the difference between parallel case and full case? Just I have explained now. Same thing. Both are similar. Just you can work on it and let me know. Okay. So I think everyone got clarity till here. Any doubts?
Ma'am, I have a doubt. Like case X and case Z seems to be similar, right? If case X means either they can be 0 or 1, X means, right? And here also it seems like it is the same as
but
case
X. We use only in the priority cases, priority encoders like that. But here, whenever you want to generate the parallel values, okay, there we will use this. Suppose 1 as I have written here, 1,000, 1,001, 1,010, like that. Instead of these 3 question marks, we will get 8 combinations, right? In all those 8 combinations, whenever you want to put some default value, then you need to use this 0, 0. For example,
Okay.
I will show, wait.
Okay.
Here output is a 2-bit size, and I am taking as a suppose 3-bit size, 3 down to 0. So n will be the 3 down to 0 here. 3 down to 0 means what? 16 combinations will be there. Okay, in that 16 combinations, we have used only 4 combinations here. Add will be 0, 0, 0, 0. Subtraction will be 0, 0, 0, 1. XOR will be 0, 0, 1, 0. And end operation will be 0, 0, 1, 1. Only 4 cases we are using. Okay. Then what about remaining all?
Remaining all will use the default value, right?
You can put as a
In
default value, or else you can put like question mark, question mark, question mark, question mark.
okay.
Z is equal to some any operation or whatever, a into b. Means what? Wherever it generates some all 4 means 0 to 15. From 0 to 15, it will assign this value only. But in 0 to 15, we already covering 4 scenarios. Other than those 4 scenarios, you want to check. Suppose in that case, what we need to put? These 2 scenarios, 0, 0, 0, 1, 1, 0, 1, 1. Like that, in that cases, parallelly you are sending some data. Okay. Or else question mark 1, question mark, question mark. So in this case, you are assigning Z equal to some value A by B. So instead of writing all 16 scenarios, at least we are covering parallelly these scenarios. 4 scenarios we can cover at a time. Okay, so in that cases, these parallel cases will be helpful.
Yeah, ma'am, got it. So it's for our design, making our design easy, right?
Yeah, it's totally design only.
Okay. Thank you.
Others, any doubts? Okay, so where we left in latches, not in latches, user defined primitives. So instead of case, we are writing the table here. Okay, but in case, you already seen, we have kept some control signals, case of control signal, but here we don't mention any control signal, just we put the truth table. Okay, and in the top level, okay, here okay, here question mark, I just explained for case example, right? So same here also, same. So 0, 0 question mark, 0, 0 question mark means what? 0, 0, 1, 0, 0, 0. For these 2 cases, we are assigning a value 0. Okay, like this here, 0 question mark 0, 0 question mark 0 means 0, 1, 0, 0, 0, 0, 0. For these 2 cases, we are assigning the value 0. And here, question mark 0, 0. That means 0, 0, 0, 1, 0, 0. These 2 cases also we are assigning output as a 0. Next, double 1, this case. 1, question mark 1, question mark 1, 1. Okay, so without generating multiple values, we are just putting like this. So how many combinations we are reducing if we put like this? Compare. So here if you see 1, 2, 3, 4, 5, 6, 7, 8. Total 8 lines. But here 1, 2, 3, 4, 5, 6. Only 6 lines. Within six lines, we are able to write the truth table. So at least we reduce the 2 lines. Okay. So that is how we generate the parallel cases. Did you all understood?
Yes, sir.
ALU code.
Yeah, tell.
ALU code.
What?
ALU, arithmetic logic unit code.
Ah,
Case statement. Using
okay. I need to show now.
yeah.
Okay.
Here you assign for add equals to binary.
Add is equal to.
Just move up for the parameter.
Ah.
Here you given add equals to binary.
Can you speak loudly?
Here you given add equals to ADD equals to 2 binary 4-bit size, which is 000.
Mm.
If I want 126th bit, actually here n we declare 128, right? For 128 8 bits size we have to give, right?
Yes.
So
Need to
if I want,
declare that.
so if I want to in case statement, if I want to use 126 bit size,
Mm.
so for that I need to put remaining all question marks.
For remaining all question marks. It totally see. Okay, in that 128 bit, if you put the question mark, will all those scenarios having same output? Suppose if you see here in this example, 8 bit, 3 bit in the sense where we are getting the zeros commonly. You need to check output where you are getting the same output. For that, we can take the inputs as a parallel, like question mark we can put. Suppose 0. Okay, see here. These two cases are there. 0, 1, 00 and 101. Suppose instead of these two cases, I am putting 10 question mark is
Maybe
equal
0
to
or 1.
what value I need to assign. Both are different. 0, 1, both are different. So I cannot add one particular value because both outputs are different. So in that cases, we cannot consider. If all outputs are same, then we can take the parallel case. Is that question? Is that what you are asking?
Yeah.
In the same way, 128, you are asking for 128. Directly we put in the case, but with Verilog test benches, we have lot of disadvantages. We never use Verilog test benches in real time.
126 bit means it will come nearly 8 bits, right?
Mm.
Like if we convert it binary, it will come some 0, 1, 1, 0, 1, like that it will
Then
come.
you can assign decimal value directly, or even hexadecimal value you can assign.
In the separate parameter we will give for that also, and we will just add hexadecimal to that. And
Suppose here what I mentioned, 2-bit binary 0000. Instead of suppose 128. 128 means how many bits you need to understand that also. Suppose 128 bit. Each value you are taking 4-bit size. Then if you are mentioning in a decimal, you can put like a 9-bit
8 hexa, it will come 8 bits.
or else octal. If you are taking octal or even hexadecimal you are taking, then you can mention
8
4,
hex.
4, 8, 12 bits. Each bit is a 4-bit size. Each value is a 4-bit size.
For 126 decimal, we will get 8-bit width, not 12, 8 bit.
Okay.
8
8-bit hexa 128 or even 127. Like that we can assign.
So in that case, we just come to the case and just given add, and then we perform the operation.
Yes.
Okay,
Yes.
thank you.
Okay. So in the top level, whatever the primitives we have written for sum and carry, we will connect in the full adder top level. So module, full adder, output sum, carry, ABC or the inputs, input, output, and sum, whatever the name, UDP sum is the name of the primitive, and UDP CY is the name of the carry primitive, and mentioning here. We can also write the test bench and we'll check the output.
Ma'am, I have one doubt. In UDP, output is also scalar.
Yes.
Okay, so we can't design any priority encoder in UDP, right? Because we'll get 2-bit
There are
size.
multiple outputs will be there, right? For every output, we need to write the primitive like this. If there are 10 number of outputs, we need to write a 10 number of primitives. Actually, we don't consider this model anywhere. In a practically, we write only in a behavioral modeling and final state missions. We never use this. But as a concept, you need to know. That's it.
Okay, ma'am. Got it.
Okay. See
Thank
here,
you.
UDP for sum, it's a primitive, whatever I explained in PPT. And for carry, also it's a primitive and full adder. Okay. So this is how we connect module, full adder, and test bench. Test bench is the same. You already know how to write the test bench. For I equal to 0 to I is less than 5. Delay is equal to $random. We are doing the randomization. Randomization concept we will discuss in the verification concepts. Okay. So delay equal to $random. Here also hash delay equal to hash delay a equal to $random. Normally we write hash 5 a equal to some value, hash 10 a equal to some value, hash 15. So that hash 10, 15, those also we are doing the randomization here. Delay equal to $random. Even delays also we are doing randomization. If you don't want, you just mention hash 5, hash 10, hash 15, a equal to $random, b equal to $random, c equal to $random. Why we are writing the $random in the sense? Before all examples we have mentioned like a equal to 10, b equal to 15, or c equal to some value. So hard coded values we have kept. Okay. So if you put hard coded values, we cannot check every corner case scenarios. Okay. So to check every corner case scenarios, we use $random. Okay. But whatever we use the $random in Verilog, it doesn't work much efficiently. We have lot of limitations with the $random. We will discuss those things in coming sessions afterwards. Okay. So those limitations we are going to avoid in the system Verilog. System Verilog is one of the perfect language for randomization and constraints. Okay. But here it just introduction how we can do the randomization. So here we don't put any hardcore values. For how many values you will put some hardcore data? If it is a 3-bit data means we can get 8 number of values we can assign. If it is a 4-bit, 16 number of values also we can assign, even it takes some time. But if you go with the 5-bit size, 6-bit size, 32-bit size, we cannot assign some hard-coded value. We need to do the randomization. Randomization means internal simulation directly generates some value. That's what we call as a randomization. Random value it will pick by the simulator. Okay. So we will discuss that thing very clearly in the verification concept.
Prasanti, one small doubt there.
Tell.
Here the dollar monitor, I mean, this doubt can, I mean, I think you have explained it also, but still, this dollar monitor you have used, I know like dollar monitor is used to, it displays all the things, not like dollar display. So the for loop you have mentioned after the dollar monitor, will it display the random values of A, B also by above dollar monitor?
Yes, actually we need to mention dollar monitor after initial block, then only it works properly. I already tried many ways by putting dollar monitor in the middle or even last of the block.
Yeah.
But whenever we put at the starting of the block, it works perfectly. So it will monitor all, even it's a loop, inside the loop values also it will be monitoring.
Okay. Okay. Yeah, that was my doubt. Like,
Yeah.
will it? Okay. Yeah.
Because we are writing within the initial block, initial begin and do.
Mm.
So whatever the changes are there within this initial block, it will do monitor. If you write outside this block, it won't do monitor. It won't check. Within the initial block, even if you put any loop, always loop, if you put always or if else, whatever, it do the change. Every change will be monitored.
Okay. Mm. Sure. But
If
if
you write
dollar display only the one, whatever the previous statement is there, that only
it
it
just
will
print the
display.
immediate value,
Mm.
just
Yeah.
single statement. Okay,
Mm.
so just go with the output A, B, C, and some carry at 0 simulation time, at 4 simulation time. These are all random values: 0, 4, 5, 10, 15, 28, 33, 38, 40. These all are random value. So if you want to give some hardcore values, we already did that thing. I'm just removing here delay dollar random, and here also, and here. So instead of this delay, I'm just adding 5. So it will be given only 5 delays. 5 plus 5, 10, 10 plus 5, 15, 15 plus 5, 20, like that. Okay, it don't give like this G4, 28, 33, 38. So we'll do simulation and check.
Can you explain that the dollar random keyword once again?
Yeah.
Why?
So if you see here, 0 and then 10. A, B, C. Okay. A, B, C are changing at 10. A equal to 0, B equal to 1, C equal to 0. Randomly. Those are generated randomly. And 15, 10 plus 5, 15. 15 plus 5, 20. And next 20 plus 4, 20 plus 20, 40. 40 plus, here we didn't, okay, it is generating in a loop. Okay, fine. We'll see the delays again. So what is a dollar random in the sense, before all examples, if you see, directly we assign A equal to some 10 or B equal to 101, C equal to some value. Okay. So if you want to cover all the cases, suppose 3-bit size means 8 number of values will be there. We need to assign 8 number of combinations. If it is a 60 bit, if 16-bit or a 4-bit size means 16 combinations. 6-bit means nearly more than 60 combinations will be there. Every time we cannot assign hardcore values. We will check only for few conditions. Randomly, we will just assign some hardcore values. Okay. But in industry, whenever we are writing some test case, we need to check every corner case scenarios. Every corner case scenarios. Okay. So those corner case scenarios we never generate by assigning some hardcore values. We cannot assign, right? If it is a 128-bit data means 2 power 128 values we need to assign. Okay, so how we will assign directly as a human? We cannot do that. Okay, so that's why we use dollar random here. Dollar random means within the range. If you declare A as a 2-bit size, within the 2-bit size, whatever the combinations available, dollar random will generate the random value. Like that, if you mention A as a 10-bit size, whatever 2 power 10 number of combinations are there within that range, dollar random will do the generate the random value. Every simulator have different random values. We cannot tell it will generate only this fixed value. We cannot say like that. Every simulator generates some random values. Okay, did you understood now?
Yes, yes, got it.
Okay. So these delays or internal delays also working, middle delays or not printing properly. We will check that thing. So next, everyone understood what is meant by UDP, and also here next example is for sequential logic circuit. In sequential logic circuit, we use a clock, right? Positive edge of the clock and negative edge of the clock. So here, if you see positive edge of the clock means like this, 0 to 1. Negative edge of the clock means like this, 1 to 0. So that's how we write here. This one J, K, clock, clear, and output. Okay, so just check the values and once practice the program, okay, you will get understand each one. Any other doubts still here? Anyone? This one I will give you more clarity. I will send you the truth table again for which values it is substituting here. So you will get clarity and try for shift register, serial input, serial output shift register. However, we design here full adder, same even multiplexer also. If you see here, multiplexer output, it will have only one output. So S0, S1 are the selection lines, I0, I1, I2, I3. Okay. Any doubts in the UDP? Everyone? Sumalata, Tarun, Sai,
Clear, Prashanta.
Vinita, Sagar, Lahari, Akash.
It's fine.
So, okay. So today we will stop till here. Okay. Because actually I don't want to take the session today because of festival. But okay, why don't we waste at least I can take 1 hour. So that's why I took the session today. So we'll stop here and in the next session we will start with the verification concepts. Okay. Okay, that's it then. I will share you one test, online test, whatever we have completed till now on blocking assignments, non-blocking assignments, these loops, case statements, everything. I will share you the online test so everyone attempt that. Okay. Once practice all the topics and then attempt. Okay.
Sure.
Okay then. Thank you all. Bye.